So if I have two sets of data that are correlated, I want to create a model for how they relate. The idea of regression is to create that simple linear model. The idea is to say, oh, I have this y, response variable, that I believe depends somehow on this predictor x. So if I tell you what the value of x is, we should be able to use that to predict a value of y. Ideally, this is a straight line. It's a straight line. What's the equation of a straight line? Algebra class was a long time ago. It's the equation for a straight line. Right. What are M and B? Aha. Intercept. That means it's intersecting something. What does the intersect with? What is it? Yeah, well, yeah, what is the y-intercept? That's a point, right? So it's the point where the line intercepts. Very close. The axis, the y-axis. So this is a point where x is 0 somewhere on the y-axis. Ideally, I don't know. Maybe there. In this case, we talked about, back in algebra, we talked about dependent and independent variables. The independent variable was the one we had control over, and the dependent one was the one that responded to that. Wait a minute, we called it a response variable. There's the connection between the two. So I have an independent predictor variable and a dependent response variable. So my real goal now is to interpret these. What does this mean? Now, in a lot of our textbook examples, we'll actually see this written differently. We'll actually see it written in the reverse order. I'm adding, I don't care what order they write it in, that doesn't really matter. But if I've written it this way, I still want to be able to interpret this. For example, I'm going to use some data. I'm going to predict the value of a home based on its area in square feet. Oops. That should be 125,000, not 150,000. It's the 150 is here. So let's interpret this idea and let's make some comments about what these numbers represent. Not just mathematically, but in actual terms of the setting of this problem. If I tell you that home price is 125,000 plus 150 times square footage, that 125,000, what does that represent? The minimum. Because I don't know of any way to buy a house with negative square feet. So square feet's got to be at least 0. And if I buy a house with no square feet, I'm buying an empty piece of land, right? So that 125,000 would represent the land price in this area. And then this 150. What's this 150 mean? per square foot. So if I told you I'm going to buy a 2,000 square foot house, what should it cost me? Say that again. Aha. 125,000 flat plus 150 times 2,000. That's another 300,000. Add that and I get $425,000. In some situations, our y-intercept has a meaning in the problem situation. Like here, the y-intercept, that $125,000, we said, oh, that would be the price for an empty lot. That would be a house with no square footage. So here's a question. This equation relates the number of car thefts per 100,000 people to the median age of the population in that area. Ooh. All right, wait a minute. Car thefts per 100,000 people related to the age of the population in that area. What does this number mean?
For every year older the population is, there's that many less car thefts.
So the number of car thefts goes down by 35.3 on average. Every year older the population gets. Does this number make sense in this context for a population? That's the y-intercept. So that would be when the median age is. Does that make any sense? Do you have a neighborhood where the middle age of the population is nothing? Yeah, I don't have negatives, so I can have the middle be at 0 if there are any people in this neighborhood. So this 1667 isn't really useful to us here because having a median age of 0 isn't particularly realistic. If I'm in a neighborhood where the average age is, sorry, the median age is 24, what is the number of car thefts in that area per 100,000 cars? I take the 24, put it into the median age, 1667 minus 35.3 times 24, 819.8. Okay. I would really like to know where this equation came from. And the way I get this equation depends on what type of regression analysis I do. I'm creating a linear model. But notice that this linear model has something extra compared to the linear models we were just looking at. This epsilon on the end here, I've seen that in my models for the ANOVA. That epsilon was an error term. And I'm going to use a regression equation that assumes that the error is normally distributed with a mean of 0. And I'm going to go a step further. And I'm going to assume that for all of the x's I was looking at in the data I gathered to create this model, they all have the same standard deviation. So for me to go around and survey a bunch of houses to figure out what the average home price is in an area, median home price versus the square footage, I go and I can look at the database of housing sales in Greensburg. That's actually publicly available. I can tell you every single house within the city limits of Greensburg, what was the last price it sold for, and how big is it? I can get that information right off the county website. What I then can do is I can predict from each of these x's a y I want to see and measure the residual. This is a simple regression model. I'm assuming that that error is 0. And I get a predicted variable, predicts a value, yi hat, for each xi in my data. So I gathered all the actual data. Let me show you a graph. It's easier if I look at a graph. Here's my linear equation model. You'll notice that there's a per value dot and there's this little normal curve next to each one. I'm assuming that the center of that is 0 and that the variation is the same across all of these. I take the x values, I plug them in. I get a dot on the line. This dot right here that's y2 hat. Why is it y2 hat? Because x1 would be the leftmost value. This is the second value. That's x2. But y2 itself is actually up here. The residual is the gap between those two. I have all of these different options here. And I'm going to look at the residuals. And I'm going to ask, how can I get a manipulation to get the residuals to be small? I'm going to adjust the slope and the intercept of that line until I get smaller and smaller residuals. Advantage. To actually do these calculations by hand is a pain in the ass. All of the equations for this are here on page 469. I'm never going to do them by hand. I am going to get the equation values for B0 and B1 from the computer. Let's take a look. 13? Yes, this is 13. Share. Here is that set of data about median home price. But notice, we're looking at home prices now, not against square footage. We're looking at home prices against income level. I go to a city, I ask, what's the median income in this city? I go to the payroll information. I go to tax records. I say, how much do people make in the city of Greensburg? And then I say, okay, go to real estate records. What's the median home price in the city of Greensburg? And I plot all this information in a scatter plot. So I'm going to take all of this information and I'm going to insert a scatter plot. Here we go. Here is our information in a scatter plot. Before I do anything else, do we have a relationship here? What do you think? Are these two items correlated? The yes, no question. As median income goes up, these kind of look like they're clustering upward as we go from left to right. All right. I hope that's right. But how can I tell? I can ask Excel to generate for me a regression model. I'm going to right click on one of the data values. When I do that, a bunch of options come up. We did this back in chapter 3 a long time ago. But way down here is the idea of a trend line. I'm going to add that trend line. Hey, there's a trend line. That line that we see, that dotted line, that's our regression line. As a matter of fact, over here on the right, a menu just popped up with format options for the trend line. I am only using linear regression, and that's why what is checked in this format section is the linear box. There are other models. There are ways to turn exponential, logarithmic, polynomial, moving average. All of those can be done as analyses. We're only looking at linear regression. I didn't name it. You can customize the name if you want. You can move the line past the edges of your data. We can use this to predict a certain number of values forward or a certain number of values back if you want. But I would actually like to see the equation. And notice way down here at the bottom, there's an equation. Display equation on chart. Click. Grab the equation. Let's move it so we can see it. Aha. I'm going to go with 2.61 plus 51.26, 25. All right. What does this mean? let's do the same analysis we were just looking at. That 2.61 times X. What does that mean? That's our slope.
$1,000 increase in income, there's a $2,000 increase in home price.
Because unfortunately, that list over there is actually given in dollars. Right? Those are in single dollars. Those are in single dollar. Those are in, oh no, these are in points. You're right. They're in thousands. So for every $1,000 increase in income, we have a corresponding $2.6 thousand increase in home price. So as incomes go up, home prices are going up. Home prices are going up more than incomes are. For every $1,000 increase, we have a $2,600 increase in home price. Home prices are outpacing income growth. What does that 51.2 mean? Okay, it's the y-intercept. But what does it mean in terms of home prices and income? Awesome.
Your income zero, cost $1,000.
But that's the average income, median income in a city, right?
Yeah, yes.
Can we have a median income in a city of zero? It would look like a bombed out horrible place, wouldn't it? I don't want to think about that. So I'm going to say that in this case, unfortunately, that intercept doesn't really mean much because the situation doesn't make sense to have a median income of zero. It is the y-intercept. If I were to trace this line all the way back here, we should hit right there, just about 51,000. But I didn't extend the line. I can. So what if I were to say, let's pick an income level? I now go to, I go to Waxahachie, Louisiana. Lovely little town. Horrible little place. I drove through it between Baton Rouge and New Orleans once. It's a spot on the side of the road. I'm going to say, let's suppose the average income, the median income in that place is $50,000. The median income is $50,000. How much should a home sell for? What do you get if the median income is $50,000? If I put in the number for our regression equation, I just put in that 50 where the X was, 181.7, $182,000. Little tiny place in nowhere in the middle of Louisiana. Okay, that's expensive town, right? Expensive to buy a house there. if you've done financial mathematics, there's a mortgage calculation available. It's available on here. There's a financial solver on the calculator. How much $181,000 house going to be a month? At current interest rates on a 30-year mortgage, you're probably talking somewhere around $2,000 a month. If you're making 50 grand a year, what's your monthly take-home pay? About 4 grand. If the house is $2,000 a month for the mortgage, that's half your income. Housing's expensive-ish today. When I first bought a house, I was told you should spend a quarter of your income on your mortgage. I've been told nowadays that 40 to 60% is not unreasonable. That's a lot of money. And that's why we get better educations to get better jobs to try and make more money so we don't have to live renting for the rest of our lives. Now, again, there is a lot of math to do here by hand. If I really want to try and do all of this, most of this information comes from trying to minimize my residual error. And that, when I say I want to find a minimum of something, my brain says, hey, that's a calculus problem. But this is a calculus problem in 2 variables, and that makes it a Calc 3 problem, and we are not doing calculus. So I am not actually going to do this by hand ever in this course. Here is the set of calculations done for the example, looking at the relationship between study time and exam score. That is just ridiculously complicated. And down here, they've given me the actual plot, and you can see the residuals they've put in there. And I think that's worth looking at, but I must tell you, actually doing these calculations is basically useless by hand. The reason a lot of these formulas use squares is so that we can actually not worry about whether the residual is negative or positive. I don't care if the predicted value is above or below the actual value. I just care about how far away it is. So we end up doing a bunch of distance. And then I can say, well, all right, how good is this model? Let me go back to the example we were just looking at. I could ask how this correlates, right? I could look at my correlation number. So I could, over here somewhere, say, do the correlation between income and home price. What's that mean? That's my R value. What we talked about on Monday. What's that R value represent?
There's like, there is a positive, but it's not like that strong.
Because we're looking at a number between 0 and 1. The closer we are to 1, the stronger this relationship is. The further we are from 1, closer we are to 0, the worse this is. It turns out that I can actually do this on here as well. Let me go back to that trend line. So I'm actually going to click directly on the trend line, go to the Format Trend Line menu again, and way down at the bottom, under that display equation on chart, It says display R squared. Ooh, I'm gonna click that. It goes right up there next to my Y value, my equation. Grab your calculator, take the square root of 0.3399. What do you get? Hey, look at that. My R value down here. 583. Close enough, isn't it? Because that was rounded to 4 decimal places and this isn't. That's pretty good. So this number R squared up here is actually the square of my correlation. Why is it squared? Well, it turns out that this square idea, this R squared idea, is called not a correlation coefficient, but a determinative coefficient, or a coefficient of determination. And it tells me how much of the variation in Y is due to the variation in X. This is actually a really important idea, so I want to write it down for a second. R squared coefficient of determination tells me how much of the variation in my response value is due to variation in my independent variable, predictor variable. Percent of variation explained. Our R squared was 33.99%, or point, let's call it 34%. That means that 34% of the house price change can be directly attributed to the income of that neighborhood. What about the other 66%? The other 66% could be due to anything. It could be due to the square area of the city not being large enough to build more big houses. Maybe they're stuck building up instead. So you get like 3-story houses on quarter-acre lots. Or you've got very different kinds of other factors that are things not technically related to our predictor variable. Take a look at a different example. Here, wait, that's the same example. Stop, back to Excel. Close that sucker. This is the example on exam scores that's in the textbook. We have that on our Canvas page share. I want to look at this one, DMV waiting times. Share number 19. Here we go. Bing. Okay. Again, there's not a lot of information here, but let's actually walk through what we get. Insert scatter plot, wait time for vehicle registrations, number of windows open. Create a trend line. Down here, I'm going to say, show me the equation and the R squared value. There's that information. Okay. What does this mean? What does that R squared value mean? We're talking about a relationship between the wait time at the DMV versus the number of open windows. My correlation of, my coefficient of determination, R squared, is 0.537. 53.7% of what?
The 53% of the variation in wait time is going to be attributed to the variation in windows open.
Exactly. 53% of the variation in wait time is caused by or due to, related to somehow. I shouldn't use caused. It's not caused, it's correlated. Is related to the number of windows open, which means that 46.3% is due to other stuff. Maybe some people have more complicated registration procedures. Maybe they're slower clerks, who knows? But 53% is simply determined by the number of windows open. I can do the calculations by hand, but I didn't bother, and there's the same thing I did earlier. One more. Let's look at a larger set of data. I have here returns on mutual fund portfolio. Last year's return versus this year's return. If I did well last year, will I do good this year? But if I look at a scatter plot, kind of looks like it. Let's look at the trend line. Yeah, that trend line's going up. The better I do last year, the better I'll do this year. Let's see how much better. Here's my equation. Here's my determination coefficient. How much better will I do this year if I did better last year? I've got three numbers up there. I've got a slope, an intercept, and a coefficient of determination. Which one of them tells me how much better I will do this year based on how much better I did last year? Max?
So
It would be the slope. And that means that for every % better I did last year, I should expect to do 0.46% better this year. How much of the variation in this year is explained by the variation last year? That's my R squared, my coefficient of determination. Perfect. Whew. So I can look at this and I can say, hey, I'm going to do better, but there are lots of other factors. 72% of the variation this year is not due to variation from last year. It's due to other market forces. So once I have this data and this information, I could ask about standard deviations, right? I made the assumption that the standard deviations were all the same. For every X value that I gathered, I could ask, we've gotten two numbers, right? I create a scatter plot here, insert scatter plot, add trend line, give me the equation, give me the R squared, There we go. Here's my information for this study time versus exam score. How much of your exam score variation is strictly due to your studying time based on this data? That's our R squared, 39%. Which means that, again, 61% of the variability in exam scores is not related to how long you studied. For each additional hour you study, your exam score is expected to go up how much? Hmm, 2%.
Oh,
Yeah, no, that's exactly right. 1.9, almost 2%. It's not a great return on investment, is it? I think there are some other variables here I might want to look at instead of just how long did you spend studying. Time spent is easiest to measure, but it's not always easy to analyze. It doesn't always give me good information. Because I see somebody here who studied an awful long time, 8 hours, didn't do very well. Somebody who studied 15 hours did better, but not as well as this other person who also studied 15 hours. I got 3 numbers here. I got a slope, an intercept, and an R squared. The R squared comes from the residuals. But the slope and the intercept were calculated values using those big long formulas that I kind of glossed past. So I could ask, what's the error in both of those numbers? How confident am I in both of those numbers? I'm not going to do this information by hand. I can do an ANOVA. There are my residual calculations. There's my averages, my squares. I can do all of this, and I can get my R squared and my R, my slope and my intercept. Those are the same numbers that come off of here. That's disgusting. I don't want to do this by hand. But then I can look at standard errors. I don't want to do this by hand. So how do I do this without doing it by hand? I'm going to go back to our data analysis. So under data, I'm going to go to data analysis. This time, I'm going to look at that regression mark. So I click on regression. Okay. Input Y range is first. Response variable is first. Which is my response variable in this case? What is the thing I am trying to predict? The exam score. So I highlight the exam scores. My predictor is the number of hours studying. Notice I highlighted the label in each case. So I'm going to tell it, hey, there are labels here. I can ask for a lot of data at this point. I can get this to do a lot for me. I could ask it for the standard errors. I could do an error for the slope. I could do an error for the intercept. I could ask it for a confidence interval. How confident am I on the true average slope and the true average intercept being the numbers I came up with? I can get a confidence interval. I'll give it 95% as a confidence level. My alpha's 0.05. And we'll put all this information in a new worksheet. Click OK. Holy mackerel, look at all this junk we got. What the hell is all of this? Oh, wait a minute. If I'm doing a confidence interval and I'm doing a test for something, I've got an F value, I've got a P value. So I've got a significance of that. That's a P value. They're over here. I've got P values as well. I've got confidence intervals lower and upper, lower and upper. Now it's the same one in this case. It automatically generates the 95%, but then I check that other confidence interval. If I change that, it would give me the other one in the second set of data. What the heck just happened here? I'm testing a hypothesis. When we did our correlation, what hypothesis were we testing? On Monday.
No correlation.
That the correlation would therefore be zero, right? Here, I could create a null hypothesis that I expect the slope to be zero. And then the alternate would be I expect the slope to be non-zero. Or I could do a one-tail test. I expect the slope to be positive. That would be my alternate hypothesis. So the null would be less than or equal to zero. Or the other way around, if I expected it to be negative. I think the more you study, the better that'll do your grades. So I would expect the slope to be positive. I could then do a one-tail t-test. Oh, look here. T-values. Lo and behold, I did t-test. And it gave me the p-values to go with them in the very next column. Notice that each column is labeled by what it is. Sorry, each row is labeled by what it is. The first row is the intercept. That p-value is 0.001. Should the intercept be 0? P-value is 0.001. Do I accept or reject the null hypothesis? Reject. Which means I'm absolutely confident that the intercept should be non-zero. Look at the confidence interval. The confidence interval says I'm 95% confident it should be between 26 and 72. That's definitely not including zero. On the other hand, study hours. That was our X value, right? That means that the number here is the coefficient for the X value, the 1.96. And if I go back and I look at my scatter plot, 1.96, that's the number next to the X. Good. What's the p-value there? Point 0.05. 0.052, really. But I said I expected the slope to be positive, right? This by default does a two-tail test. I'm telling it to do a one-tail test. What should I do with my p-value? Which means that p-value is 0.1. I should reject, which means, sorry, I shouldn't reject. It's too big. But the slope was 1.96, and my confidence interval goes from negative 0.02 to 3.9. Okay, zero's included in that, right? But it's way over on the edge. I'm just barely not convinced that this slope is wrong. But I can't statistically significantly say, hey, studying more makes your exam score go up. I don't have the ability to conclude that, because that slope could be zero. It's a really slim chance it's zero, but it could be zero. Crap. The more you study, the more you know. The more you know, the more you forget. The more you forget, the less you know. The less you know, the worse your exam grade is. I don't know for sure whether or not more studying helps. That means it might not be hours spent. It might be the way I study that matters more. We'll talk more about what this information can get, what I can get for overall fit, and whether or not I should trust these results on Friday. I'm gonna do almost all of this work in Excel, not doing this stuff by hand. I will see you all then. Have a wonderful rest of your day.